So now we get to the good bit where we can add dispersion to our system. We'll start with a wave with just two frequencies, so we have the cosine with k1 omega 1 and cosine with k2 omega 2 again. But now the ratio of omega and k is not the same across these two frequencies, and that's because we have dispersion. Taking the Fourier transform, we once again get two pairs of delta functions at plus or minus k1 and plus or minus k2, so that's these two pairs here at the positive and negative frequencies, and they'll be rotating around. Now we can hit the animation button here. We see our wave moving in real space, in x, and we can see the shape is now changing as it propagates, and that's because these two waves are changing their relative phase as they move. So they're adding up to give us a different shaped wave at each time step as it propagates. Over here in Fourier space, things don't look so different. The components here are still rotating around in the complex plane, and they're still rotating at different speeds. The only difference now is that the speed of rotation here is not linearly proportional to k, because this ratio is no longer constant. We can't really tell just by looking at it that's the case, but we know it to be the case because we can see the wave changing shape here in real space. So a time shift, remember, rotates the phase in Fourier space. So the time shift here, t, rotates it by an amount omega I times t, that's these shifting exponentials here. We can rewrite omega as ki times ci, and ci times t is now delta xi. So for a given propagation time t, the distance at which each of these k components moves is different. So that's just telling us that they're moving at different speeds. So the ratio of omega I and ki is not constant, as we have different speeds for each frequency. So the two frequencies do not travel the same distance delta xi in a given time interval delta t.